All right, so today we are going to talk about circuit analysis in the frequency domain. So in our last class meeting, we analyzed the following circuit where we had a current source, IS of t, connected in series to a 5 ohm resistor, which was then connected in series to a ½ Henry inductance. And we tried to solve for this voltage Vs of t, where Is of t, if I'm remembering correctly, was 2 cosine five t plus 0 degrees amps. And if I remembered that incorrectly, please let me know. And what we found doing, let me spell things out here, really. We found the voltage drop across the resistor. We found the voltage drop across the inductor, where VR of t was 10 cosine 5t plus 0 degrees volts. VL was negative 5. I think it was, oh, give me just a second. Positive 5 sine 5t plus 0 degrees volts, which would be the same thing as, no, it was negative 5, sorry. Getting mixed up with things. Which we could convert to 5 cosine. So let's see, add 180 degrees, subtract 90 degrees. So this would be 5 cosine, positive 5 cosine 5t plus 90 degrees volts if we were so inclined. And then we used complex numbers to effectively add those two signals together and found that we would have, let's see, we could express the voltage drop across our source as a single sinusoid with a value of 11.180 cosine 5t plus 26.565 degrees volts. And in order to sort all of those different things out, we had to use a little bit of trig, a little bit of calculus, and not a whole heck of a lot of circuit theory. The only circuit theory that we really applied was Kirchhoff's voltage law, which told us to add those two signals together to get the source voltage. Everything past that was trig and calculus. So what I want to do today is to see if we can't figure out a way to get rid of some of that pesky calculus and make a method for solving sinusoidally excited circuits that looks a lot more like the circuit analysis that we are used to. So the first thing that we are going to do is we're going to formally introduce the topic of phasors, which is actually something that we kind of did on Monday's class meeting. I just didn't really call it that in particular. Okay. So phasors are a shorthand notation for describing sinusoidally varying signals. So we know that if we were to have a voltage waveform, V of t, of the form Vm cosine omega t plus some phase angle, I'm going to call this theta v, where that subscript v just means this is a phase angle of a voltage, or a current I of t of the form Im cosine omega t plus some phase angle theta I. These are what are called time domain representations of our signal. Okay. So if we were to hook up an oscilloscope to measure a sinusoidally excited voltage, we would literally see a signal that is mathematically modeled by that equation. So let's just make a note here. Time domain signals. Well, I showed in our last class meeting that these time domain signals were just the real part of a complex signal, right? So this voltage would be the real part of a complex signal Vm e to the j omega t plus theta v. And similarly, this current would be the real part of a complex current waveform, e to the j omega t plus theta I. And I'm going to call these complex signals mixed domain signals. And I'm calling them mixed domain signals because they're somewhere in between, or they're an intermediate step between the time domain that we experience in our everyday lives and the frequency domain, which is just kind of a made up mathematical space that we use to analyze sinusoidally excited circuits because the math is much, much easier. So we can go from the time domain into the mixed domain simply by converting our time domain signal, which has a particular magnitude, a particular angular frequency, and a particular phase angle, into the mixed domain by just writing that exact same signal as a complex number of exponential form that has the same magnitude, the same energy, and the same phase angle. To get to the frequency domain where phasors live, we simply write our mixed domain signal as a polar form complex number, meaning that we keep the magnitude, keep the phase angle, and throw everything else away. And we'll see why we can throw everything else away here in just a moment. So a phasor voltage V is composed only of the magnitude of the time domain signal expressed as a cosine function and the phase angle of the time domain signal expressed as a cosine function. Everything else just gets thrown away. Exact same thing for our current. So our phasor current I would simply be Im with an angle of theta I. And these are considered frequency domain signals, which are commonly called phasors. So let's take a look at in-class assignment 19, problem 3, really quickly. So in this particular problem, we are asked to express the following time domain signals as phasors in the frequency domain. So here in part A, we have a time domain voltage. VA of t is -10 cosine 4t plus 75 degrees volts. So converting from a time domain signal into a phasor signal has the exact same rules as manipulating sinusoids like we went over with on Monday, meaning that we need to express everything in terms of cosine functions, and we need to make sure that everything has a positive magnitude. So for this guy right here, we can get rid of that negative sign out front simply by subtracting 180 degrees from the phase angle or adding 180, but I'm subtracting particularly here to make sure that my angle lies somewhere in the first quadrant, between negative 180 degrees and positive 180 degrees. So I just want my angle to have the smallest possible magnitude. So anyway, that would look like 10 cosine 4t minus 105 degrees volts. And then to convert this into a phasor, voltage VA, I would simply take my magnitude here, which is 10, take my phase angle here, which is negative 105 degrees, and then throw everything else away. That is literally as hard as it needs to be to convert from the time domain into the frequency domain. We just make sure that we have a cosine function with a positive magnitude, keep the magnitude, keep the phase angle, throw everything else away. So for part B here, I want you guys to provide some input, right? So we have VB of t is equal to 5 sine 20t minus 10 degrees volts. So how am I going to convert that into a cosine function first? Does anybody remember?
We
subtract
90.
90 degrees.
Actually, I think I have you all muted, so give me just a second. Okay, you're unmuted, so I apologize if anybody spoke.
Subtract 90 degrees.
Having technical difficulties in as much as I saw that Baylor talked, but I still didn't hear anything. So give me just another second. Sorry about this.
Test.
My volume is at 100%. Let me see if it's an issue with the audio.
Everybody can hear each other. He just can't hear us, right?
Yeah.
Yeah, because like I hear all of y'all talking. He just can't hear us.
Could you say that again, Austin?
Can you hear us now?
I can, but I hear you out of my monitor, not my laptop. Give me just a second. This is really weird. I definitely don't have my headphones connected this time. Somebody try talking again.
Test.
All right.
Can you hear us
Still
now?
nothing out of that one, so I guess I'll just have to listen to you guys out of my monitor, which is odd. Okay, sorry about that. So how do I convert from sine to cosine?
Subtract 90 degrees.
Subtract 90 degrees. Thank you for that, Baylor. I'm sure it's probably the third or fourth time you've said it, so thank you for bearing with me. So we're going to subtract 90 degrees from our phase angle. So that's just going to look like 5 cosine 20t minus 100 degrees. And now we have everything expressed as a single cosine function. So anybody care to venture a guess as to what our phasor representation of this signal should look like?
Be 5 and the angle sign minus 100 degrees.
Exactly right. So we kept the magnitude, angle, kept the phase angle, call it a day. Again, it doesn't need to be any more difficult than that. So we literally just take this 5, take this negative 100 degrees, and throw everything else away. For part C here, we're going to do this very similar to how we combined things in our last class meeting, right? So we're going to say VC of t is 4 cosine 2t plus 25 degrees plus 3 sine 2t volts, which looks like 4 sine 2t plus 25 degrees. Since we're just converting from sine to cosine, I'm going to do the exact same thing we just did. I'm just going to subtract 90 degrees from our phase angle. So that's going to look like 3 cosine 2t minus 90 degrees volts. And then from here, our phasor voltage VC would just be 4 angle 25 degrees volts plus 3 angle negative 90 degrees volts. And we can just add these two complex numbers together to get a single phasor that represents this signal. So 4 angle 25 plus 3 angle negative 90 comes out to be 3.85449. So 3.854 angle negative 19.86102. So negative 19.861 degrees volts. This isn't part of the in-class assignment problem, but we can convert from a polar form back into a time domain form very easily, right? So if we wanted VC of t expressed as a single cosine function, we would just take the magnitude, 3.854. We would put back in our cosine. Our angular frequency was 2, so we'd have 2t, and then we plug back in our phase angle. So negative 19.861 degrees volts, which is exactly what we did in class on Monday. So before we move on from phasors, does anybody have any questions about this?
So if you're not given the angular frequency, and let's say you're just given that 3.854 angle negative 19.861, can you convert back, or you have to be given the angular frequency?
You absolutely have to know the angular frequency in order to convert back into the time domain. That is a very, very good question. So you guys probably haven't seen this yet because I don't think I've uploaded the practice exams. But some of the questions that I like to ask you guys on a test would be something like, we put a line here. Which of the following signals could be represented by the phasor? And let's just say X is equal to 5 angle 0 degrees. And so you might have options like 5 cosine 3 pi t, or 5 sine 6t plus 90 degrees, and then I could find another one or two. But like both of these would be represented by a phasor of 5 angle 0, even though their frequencies or their angular frequencies are very different. So 3 pi is definitely not equal to 6. So that is one of the potential drawbacks of working in the frequency domain, is that we kind of throw away that dependency on the angular frequency. So to recap, if we want to convert from the frequency domain back to the time domain, we absolutely have to know what angular frequency we're dealing with. So very, very good question. Any other questions? All right, so let's pop back over here. So I think we have a pretty reasonable handle on phasors. It's not a particularly difficult concept. So now let's talk about frequency domain relationships for circuit elements. So we're going to start with a resistor, okay? So let's say that I have a simple resistor. R, where we have a voltage drop across our resistor V of t. And we're going to say that our voltage in this particular case is a sinusoidal voltage. So I'm going to call this Vm cosine omega t plus some phase angle theta v. And because there is a voltage drop across our resistor, we should expect that there's some current flowing through our resistor as well. And our current should be of the same form. So we would have Im cosine omega t plus some phase angle theta I. As mentioned before, these signals are just the real part of the complex or mixed domain signals, Vm e to the j omega t plus theta v, and Im e to the j omega t plus theta I. So what is the relationship between current and voltage for a resistor?
Just Ohm's law?
Exactly right. Just Ohm's law. V is equal to I times R. So we would have the time domain relationship. V of t is equal to R times I of t. And what I'm going to do is I'm simply going to substitute in those mixed domain signals there. And we are going to do a little bit of algebra and such, and then see what the relationship is going to look like in the frequency domain. So just simple substitution, I'm going to replace v of t with our mixed domain signal, Vm e to the j omega t plus theta v. And this will be equal to r, times our mixed domain current signal, Im e to the j omega t plus theta I. So what I'm going to do now is I'm going to split those exponential functions up, okay? So because I have e to the j one angle plus another angle, I could write that as Vm e to the j omega t times e to the j theta v. And I can do the exact same thing for the exponential on the right-hand side of the equal sign. So we'd have e to the j omega t times e to the j theta I. Well, we can see right now that there is a common factor of e to the j omega t that cancels out on both sides. So this is actually what lets us throw the omega t part of our signal away when we're working in the frequency domain with phasors. It's common to all signals, so it doesn't add any new information. We can literally just ignore it because it cancels out on both sides of every equation that we could ever possibly write. What we're left with is a magnitude and a phase angle, which is exactly all that a phasor is. So I'm going to rewrite these just really quickly here. So we would just have Vm e to the j theta v is equal to r times Im e to the j theta I. And I want us to make a couple of observations here, okay? So I'm going to do these over to the side really quickly. So what we have on the left-hand side of the equal sign is an exponential form complex number. And what we have on the right-hand side of the equal sign is also an exponential form complex number. So that means that the magnitude of whatever we have on the left-hand side of the equal sign has to equal the magnitude of whatever we have on the right-hand side of the equal sign. So we could say that the magnitude of the voltage drop across our resistor is just going to be equal to the resistance times the magnitude of the current flowing through the resistor. And the phase angle on the left-hand side of the equal sign has to be equal to the phase angle on the right-hand side of the equal sign, which means the phase angle of the voltage drop across the resistor has to be equal to the phase angle of the current flowing through the resistor. So what this means is that for a resistor, the voltage and the current are in phase. So that means the voltage isn't leading or lagging. It is exactly in phase with the current. So we have these relationships that must be true at any frequency as long as we are dealing with a sinusoidal excitation. Okay. So I'm going to put a box around these relationships. I'm not expecting you guys to remember them. It'd be great if you did. But we're going to see these crop up again and again, and we're going to use them in a couple of different places. So I'm just drawing your attention to the important parts of this bit.
So is this only dealing with one particular resistor that they're in phase?
So any resistance will behave like this. So for any generic resistance are. So it doesn't matter if it's a 1 ohm resistor or a 45 mega ohm resistor. Resistors, pure resistors, behave in this way, where the magnitudes are defined by Ohm's law, and the phase angle of the voltage and the phase angle of the current are the same.
So would that signal need to be applied at one given point in time to be the same for both of them, for both the voltage and the current?
How could you? So think of it this way. We are either applying a voltage drop across the resistor and measuring the current flowing through it, or we are applying a current through the resistor and measuring the voltage drop over it. It's impossible to have those two things occur at different points in time because they are directly related to each other in a kind of cause
because
and
of the
effect type relationship. Does that make sense?
Yeah, and that's because of the homogeneity principle, correct?
I'm sorry, I couldn't understand that.
That's because of the homogeneity principle.
So the homogeneity is about scaling. So not
Okay, man,
really.
I think I understand. I'm sorry.
Yeah, no. Discussion is fine. So, if we excite our circuit element of interest, be it a resistor, a capacitor, or an inductor, and we measure a response, like that is a cause and effect kind of thing. So if we don't sinusoidally excite a resistor, then we are not going to see any of these things. So like if we don't apply a sinusoidal voltage across it, we're not going to see a sinusoidal current flowing through it, and vice versa. If we don't have a sinusoidal current flowing through it, then we won't see a sinusoidal voltage drop across it. But those two things are 100% in phase. What we're going to see here in just a moment is that for an inductance and or a capacitance, things get out of phase. And not to jump too far ahead, but we're going to see that in an inductance, the current will always wind up lagging the voltage waveform by a fixed amount. And in a capacitance, the current will always wind up leading the voltage waveform by some fixed amount. But still, that's not the signals being applied at different times per se. It's just the signal characteristics have caused some shift or delay between them. Okay. So coming back to what we have on the left-hand side of the page over here, we have this Vme to the j theta v. So that is an exponential form complex number. And we know that we can write an exponential form complex number as a polar form complex number because polar form is literally just a shorthand notation for this. So our polar representation would be Vm angle theta v. And then over here on the right-hand side, we would have R times Im angle theta I. Well, Vm angle theta v is nothing more than our definition for a phasor voltage, V. And then we would have R, and then Im angle theta I is nothing more than the definition of a phasor current I. So what we have in the frequency domain is that V is equal to I times R. So effectively, Ohm's law is Ohm's law regardless of whether we are in the time domain or the frequency domain, which shouldn't be that surprising of a result. So just to recap, for resistors, Ohm's law still applies in the frequency domain. The magnitude of the voltage drop across the resistor will be equal to the resistor value times the magnitude of the current, and the voltage and the current waveforms are perfectly in phase with each other. Now let's look at an inductance. Let's do this on the next page. So let's say that I have a generic inductance L, and there is a voltage drop across our inductor, where once again that voltage will be of the form Vm cosine omega t plus some phase angle theta v, and our current I of t will be of the form, sorry, let me draw it on here. I am cosine omega t plus theta I. What is the relationship between voltage and current for an inductor? And I would prefer the derivative-based relationship, please.
V L of t equals L DIL of t respect to time.
Exactly right. So let me write that down here really quickly. So the voltage drop across our inductor is equal to the inductance times the derivative of the current flowing through the inductor with respect to time. So we are once again going to substitute in our mixed domain signals. So I'm just rewriting them up here for you guys really quickly. And if we substitute in those mixed domain signals, what we're going to have is Vm e to the j omega t plus theta v is equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So I'm going to go ahead and do that thing where I effectively split up my exponentials. So that's going to look like Vm e to the j omega t times e to the j theta v is equal to L times the derivative of Im e to the j omega t e to the j theta I. And the reason why I did that is because it's going to let us take that derivative on the right-hand side a little bit more easily, right? So Im is constant with respect to time. E to the j theta I is constant with respect to time. So really, all we're taking the derivative of is e to the j omega t. Well, the derivative of e to the j omega t is just j omega e to the j omega t, because it's a simple exponential function. So that means we would have Vm e to the j omega t e to the j theta v is equal to j omega L times Im e to the j omega t e to the j theta I. And once again, we can see that e to the j omega t is a constant factor or a common factor to both sides. So we can suppress that frequency term and throw this part away effectively. So we can manipulate the right-hand side of this equation a little bit further by understanding something here. So in our previous problem where we had a resistor, we had an exponential form complex number on the left-hand side. So we had Vm e to the j theta v. And on the right-hand side, we had something times Im e to the j theta I, where with the resistor, it was just the resistor value by itself. So we had exponential form complex numbers on both sides. But right now, we have a rectangular form complex number, j omega L, being multiplied by that exponential form complex number. So how could we represent that j omega L as an exponential form complex number so that we can do this multiplication easily? So let's look at a complex plane really quickly. So let's say that these tick marks, and this is the positive real direction, and this is the positive imaginary direction. So let's say that the tick marks that I've drawn on that plane represent us moving 1 unit into the positive real direction or the negative real direction, and 1 unit into the positive imaginary direction or the negative imaginary direction. So if we move 1 unit into the positive real direction, we would commonly call that just the number 1. We can express that as a rectangular form complex number, which that would just be 1 plus j0. Or we could express it as a polar form complex number, which would be 1 angle 0 degrees, or in exponential form, 1e to the j 0 degrees. So these are all effectively 3 different ways to represent the number 1 as a complex number. We could do something similar if we went 1 unit up in the imaginary direction. So we would normally call that just j, but we could also call that 0 plus j1, or 1 angle positive 90 degrees, or 1e to the j 90 degrees. Similarly, if we went 1 unit in the negative real direction, that would be -1, or let me do it up here actually. So -1 or -1 plus j0, or 1 angle plus or minus 180 degrees, or 1e to the plus or minus j 180 degrees. That 1 doesn't look like a 1. And then lastly, if we went 1 unit in the negative imaginary direction, we normally call that negative j, which would be 0 minus j1 in rectangular form, 1 angle negative 90 degrees in polar form, and 1e to the negative j 90 degrees in exponential form. So let me do it in orange. So this j right here, we could just as easily call that 1e to the j 90 degrees. So we would have 1e to the j 90 degrees times im e to the j theta I. And doing this math, 1 times im is just im, and then we'll have e to the j theta I plus 90 degrees. Oops, I forgot there's a factor of omega L here as well, so let's tuck that in. Like so. Sorry about that, crossing it all together. So now we have things where we have an exponential form complex number on the left-hand side of the equal sign, and then an exponential form complex number way over here to the right. So once again, we can observe that the magnitudes on both sides of the equal sign have to be the same. So Vm must be equal to omega L times Im. And now we can see that the phase angle of the voltage, theta V, is equal to theta I plus 90 degrees. So the phase angle of the voltage is always 90 degrees greater than the phase angle of the current, which means our voltage is always leading our current by 90 degrees, or vice versa. Our current is always lagging our voltage by 90 degrees. So anytime we have a true pure inductance, the voltage and current will be exactly 90 degrees out of phase, and the current will lag the voltage. If we had a practical inductance, meaning that the coil of wire that forms the inductance has some resistance to it, we'll see that the angle that separates the current and the voltage is a little bit less than 90 degrees, but it's always going to be pretty darn close. So in the mini labs that you guys would have worked, if you were doing a face-to-face class, you would have found that for the inductors that we have in that classroom, it was around 88 degrees. And that small difference away from 90 degrees is because of the resistance of the wire that the inductor is made of. Okay, so let me put boxes around those relationships because they are important. And then let's go back over and see if we can put things in terms of phasors. So this guy right here, Vm e to the j theta v, could be written as a polar form complex number as Vm angle theta v. And then we would have j omega L times Im angle theta I, recognizing that Vm angle theta v is nothing more than our phasor voltage V, and Im angle theta I is nothing more than our phasor current I. We have this relationship. So this is kind of an Ohm's law for inductances. But instead of just using L, we have to remember to multiply by a factor of j omega. We'll formalize that in a couple of minutes here. Lastly, let's talk about what happens when we have a capacitor. So here's our capacitance C, and we're going to sinusoidally excite it with the exact same voltage that we've been doing and look at the sinusoidal current that flows through it, right? So I'm not going to bother writing V of t and I of t again because we've done it 2 times. It's the same thing here. What is the relationship between current and voltage for a capacitor? And please give me the derivative-based relationship again.
C dvc of t equals I of t.
So exactly right. The current flowing through a capacitor is equal to the capacitance times the derivative of the voltage with respect to time. So all of the work that we're about to do here is extremely similar to what we're going to do up here, or really it's the same thing as what we would have done up here, except that the current is going to be on the left-hand side and the voltage is going to be on the right-hand side, right? So we could say that Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta v. Because we've already done this derivative, I'm going to go ahead and skip a couple of easy steps here. So we could say that this is going to be Im e to the j omega t e to the j theta I is equal to j omega c times Vm e to the j omega t, e to the j theta v. And these e to the j omegas cancel each other out. Doing this similar math to what we did before, when I multiply by a factor of j, that's just adding 90 degrees to my phase angle. So I could write this as omega c Vm e to the j theta v plus 90 degrees. And we could observe from this that the magnitude of the current Im is equal to omega c times the magnitude of the voltage. And we would see that the phase angle of the current theta I is equal to the phase angle of the voltage plus 90 degrees. So in a capacitor, the current is always leading the voltage by 90 degrees because the phase angle of the current is always 90 degrees larger than the phase angle of voltage. So in a capacitor, the current leads the voltage by 90 degrees, and in an inductor, the voltage leads the current by 90 degrees, as we saw a couple of moments ago. Okay. So putting things in terms of our phasors, we would have Vm angle theta I is equal to j omega c. Sorry, that should be Im angle theta I. My apologies for that. J omega c times Vm angle theta v, or phasor current I is equal to j omega c times phasor voltage V. So we have now figured out what our current voltage relationships are for resistors, capacitors, and inductors in the frequency domain. So we are one relatively small step away from being able to analyze circuits in the frequency domain without having to use literally any calculus or any trig identities at all. Okay. So that one little step that we still need to sort out is what's commonly called impedance. So I want to bring you guys' attention back to something that we did on the third day of class, if I'm remembering correctly. So if we have a linear black box network, like so, and we excite it with some DC source. It does not matter whether that DC source is a voltage or a current. And we measure the voltage drop across the terminals of our linear black box network. And we measure the current flowing into the terminals of our linear black box network. Then the ratio of the voltage to the current is what?
The resistance of the black box.
The resistance of our black box network. 100% correct. Okay. So think of this as a DC resistance, okay? Now, if we do the same thing, but instead of exciting our black box network with a DC source, we excited it with a sinusoidal source. So I forgot box above, but that'll be fine. Network. So we sinusoidally excite this network, and we were to measure the phasor voltage across the terminals and the phasor current flowing into the terminals. The ratio of our phasor voltage to phasor current is commonly known as the impedance Z. So the impedance Z is just playing the role of resistance in sinusoidally excited circuits. It's literally just the ratio of current to voltage, okay? So we are largely going to treat it like resistance, except that since it is the ratio of two complex numbers, our impedance Z must be a complex number itself. And so that means that we can express it either in polar form or rectangular form. So let's play around with the polar form representation, okay? First. So we would have Vm angle theta V divided by Im angle theta I. And we know that the magnitudes will simply divide and the angles will subtract. So we would have some magnitude of our impedance Z and some phase angle for our impedance theta Z, like so, where the magnitude of our impedance is nothing more than the magnitude of the voltage divided by the magnitude of the resistance, and the phase angle of the impedance is just the difference between the phase angle of the voltage and the phase angle of the current. So that's our polar form representation of impedance. More often than not, impedance is expressed as a rectangular form complex number. Okay. So in rectangular form, impedance is expressed by its real part, R, and its imaginary part, X. I'm in class. Sorry, my grad student interrupted me. So this real part of the impedance, R, is literally just the DC resistance that we are used to. Okay. And the imaginary part of the impedance is what is commonly called the reactance. Okay. So real part is resistance, imaginary part is the reactance. Okay. More often than not, impedances are expressed in polar form, or excuse me, in rectangular form. There's nothing stopping us from expressing them in polar form by any stretch of the imagination, but more often not, impedance is expressed in rectangular form. Voltages and currents are usually expressed in polar form. So that's why I'm very thankful that our calculators are able to handle both polar form and rectangular forms, because we're going to wind up using a mix of both representations in order to do our circuit analysis. Okay, so let's say that we want to know what the impedance of a resistor is. So let's call it Z sub R. That would be nothing more than the ratio of the voltage drop across our resistor divided by the phasor current flowing through our resistor. So I would really appreciate it if somebody would go back up one page or so in their notes and do that small amount of algebra to tell me what the impedance of a resistor should look like. So let me just scroll up here so I can make it super obvious what I'm expecting you to do right here. So we have this equation that I boxed in red. If I were to divide both sides of this equation by my phasor current I would have voltage phasor divided by current phasor is equal to what?
Just resistance, R?
Just the resistance R, exactly right. So the impedance of a resistor is just the resistor value itself. Okay. Nothing remotely difficult about that. Expressed more formally in rectangular form, this would look like R plus J0. So a resistor does not contribute any reactance at all. And in polar form, this would look like R angle 0 degrees. What are the units of resistance?
Ohms.
Ohms, not remotely a trick question. Okay. So now let's look at an inductance. So what would V over I phasors look like for an inductor? Let me scroll back up here. Anybody care to venture? I'm going to call it a guess, but it's the same level of algebra we just did.
J omega L.
J omega L. Thank you, Baylor. So the impedance of an inductor is J omega L. More formally, in full rectangular form, this would look like 0 plus J omega L. And so from this, we can see that inductors contribute positive reactance to a circuit. In polar form, this would look like omega L with an angle of, sorry, that should be 90 degrees. And let's look at the units here really quickly. Okay. So omega has units of radians per second, where radians are a dimensionless quantity, so we can kind of throw those away from the jump. And then inductance is measured in henries, where a henry is a volt second per ampere. And we can see that the seconds here in the numerator cancels the seconds here in the denominator, leaving us with volts per amp. Well, what's another term for volts per amp?
Ohms.
An ohm, exactly right. So the impedance of an inductor is also measured in ohms. Let's wrap things up here with a capacitor, right? So the impedance of a capacitor would simply be the ratio of the phasor voltage to the phasor current. And this is going to come out to be 1 over J omega C, which would look like 0 minus J times 1 over omega C. Let me explain really quickly where that minus sign comes from. So 1 over J times J over J looks like J over J squared. What's J squared?
-1.
-1. So 1 over J is the same thing as negative J in the numerator. So that's where that negative sign came from. So from this, we can see that capacitors contribute negative reactance to a system. And then in polar form, this is going to look like 1 over omega C with an angle of negative 90 degrees. And if we look at the units here, we have 1 over omega C. So that's going to be 1 over omega is seconds per radians. And then capacitance is measured in amp seconds. Sorry, that looks worse than my usual handwriting. Per volt. And so the seconds cancels the seconds. The radians is a dimensionless quantity. And we once again have volts per amp, which we know is just a fancy term for an ohm. So the impedance of a capacitor is also measured in ohms. So there's good news. Since the impedance of a resistor, an inductor, and a capacitor are all measured in ohms, we can effectively treat all circuit elements in the frequency domain as if they were resistances. By that specifically, I mean that we can just use regular resistance combination techniques in order to figure out what the equivalent impedance of a network would be. Before I forget about this, I want to talk about something here really quickly. Okay. This is kind of beyond the scope of this class, but I think it's very interesting, which is why I'm bringing it up. Okay. So if we look at the impedance for a resistor, we can see that it is independent of frequency, right? There's no omega listed in our expression. So it doesn't matter what frequency we're dealing with, a resistor always just looks like a resistor. If we look at the impedance of a capacitor or an inductor, however, we can see that the impedance is dependent on the value of omega. So let's say that omega is very, very small. So something approaching 0 or DC. What would the impedance of an inductor look like when omega is very close to 0?
Infinity?
So I think J times 0 times L is probably 0.
Right.
So the impedance of an inductor at DC is 0 ohms. Does that agree with anything else that we've learned in this class? So what do you guys think an inductor looks like at DC
Yes.
based on what we've learned previously?
It's a short circuit.
A short circuit, where a short circuit is characterized by having no resistance. So our impedance equation exactly agrees with what we've observed previously in the class, right? At very, very low frequencies, an inductor behaves like a section of wire or a short circuit, which means that its resistance or impedance value is 0. If we look at our capacitor relationship, we can see that its impedance is inversely proportional to frequency. So at very, very low frequencies, the impedance of the capacitor trends towards infinity or an open circuit. Okay? But we can also look at things at very, very high frequencies, right? So at very, very high frequencies, the impedance of an inductor starts to look infinite, meaning that at high frequencies, an inductor tends to look like an open circuit, and at very high frequencies, a capacitor tends to look like a short circuit. So they literally change roles as we get into higher and higher frequencies. And this frequency-dependent resistance or impedance is actually what we utilize in order to develop electrical filters, which are a fundamental building block of all our communication systems and stuff like that. So without this behavior that we observe in capacitors and inductors, our cell phones, internet, all of that kind of stuff, literally none of that would work if these components impedance did not change with frequency. So just a kind of an interesting little tidbit about these guys. Okay, before we work in class assignment 19, problem 4, does anybody have any questions regarding impedance? Okay,
I have a quick question.
yes.
Did you mean to pull on that resistor when you put it into polar form, the R and then angle sign and 0 degrees? Because I was looking on the other ones and it didn't look like you pulled this from the same spot, unless I was just misunderstanding something there.
What do you mean pulled?
The magnitude. Like the magnitude came from the left-hand side of the rectangular form
No, no,
with the
no, no. So
resistor.
the magnitude shouldn't come from the left-hand side or the right-hand side of the rectangular form. It should come, so we're just treating it as a complex number, right? So
Yeah.
just to refresh your memory for something that we learned, I think it was late last week, and we talked about it very quickly. But the magnitude of a complex number A is just the square root of the real part of complex number A squared plus the imaginary part of complex number A.
That's right. I'm sorry about that. That just wasn't jogging my memory. I'm sorry about
No,
that.
no, 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 not a problem at all. Questions are great, right? So the real part is R, the imaginary part is 0, so the square root of R squared is just R. The square root of omega L squared is just omega L, and the square root of negative 1 over omega C squared is positive 1 over omega C. So all those magnitudes are correct. All of those phase angles are also correct. Okay, number 19, or excuse me, dang it, in class assignment 19, problem 4. So in this particular problem, we are told that our network here is being excited at a linear frequency of 1 kilohertz. So if our linear frequency is 1 kilohertz, what would our angular frequency be? This is a relationship that we covered in class on Monday, by the way.
I think it should be 2 pi of the frequency, so that'd be 2000 pi hertz, or well, no, it'd be
2000 pi radians per second. Absolutely right. So we know what omega is now, because we know how to convert from linear frequency f into angular frequency omega, and it is just multiplying by a factor of 2 pi. So what would the impedance of this 25 ohm resistor be?
Is it just 25 ohms?
It is. So the impedance of a resistor is just the resistor value itself, which means we don't have to change the 25 ohm resistor, the 20 ohm resistor, or the 55 ohm resistor. We're going to leave those three exactly as they are. Okay. Now let's figure out the impedance of our capacitance, right? So the impedance of a capacitor is given by 1 over j omega c. So that's going to look like 1 over j times 2000 pi times 10 times 10 to the minus 3. And I'm leaving off the units because we know that the units for impedance should be ohms. So when I put this in my calculator, I got negative J 0.0159155 and some change. So I'm just going to leave it as this. Ohms. Did anyone else get a similar number?
How did you get the negative value?
So let me pull up the calculator thing so I can show you literally exactly what I put in my calculator. Get this thing out of the way. I'm using my TI-80 today, or sorry, not TI-80, TI-36. I want to continue with the trial version. Clear that out. Oh crap. Is my screen still being shared? Yes, it does. Okay. Clear this jibber jabber. Okay, so 1 over 1i 2000 pi and then 10 times 10 to the minus 3. Close parentheses. And I'm going to store this in my calculator as x. You'll see why in a moment. So 0.0159 angle of negative 90 degrees is the same thing as negative J 0.0159. Just to prove that, convert this, sorry, to rectangular. So once again, 1 over J is the same thing as negative J. So looks like I got that correct. So at a relatively high frequency, 1 kilohertz, this 10 millifarad capacitor, excuse me, looks pretty darn close to a short circuit, as I mentioned a moment ago. For our inductance, our impedance is going to be J times omega times the inductance value. So that's going to be J times 2000 pi times 20 times 10 to the minus 3. So let me throw that in my calculator really quickly. And that comes out to be J 40 pi ohms. So what I'm going to do is I'm just going to replace this inductance with an impedance of J 40 pi ohms. I'm going to replace this capacitance with an impedance of negative J 0.0159 ohms, or actually what I have stored in my calculator is X. And now in order to determine the equivalent impedance of this network, I treat this exactly as if it were a resistor combination problem. So how would you guys handle this thing?
Identify your nodes and then go from A to B.
Sure, we can do it that way. So
But I mean, you could look at it, it'd be a lot simpler too.
yeah, for this one, I think it's easy enough that we could kind of look at it, right? So I think the 55 ohm resistor is in parallel with the J40 ohms impedance. So that would be 55 times 40 pi times, crap, 40 pi times I over 55 plus 40 pi times I. So let me do it this way really quickly. So I'm going to call this guy R3 and this guy L, or ZL. So ZL in parallel with R3, I got to be 46.15796. So let's call that 158 plus J 20.202 ohms. I'm storing that in my calculator as Y, by the way. To that, I would add this and this in series. So that's just going to look like 20 plus what I have stored in my calculator is X. And so if we call this R2 and this guy ZC, we have R2 plus ZC plus the parallel combination of ZL in parallel with R3 looks like 66.158 plus J 20.186 ohms. And now what would I do? So just to be clear, I'm not trying to overwhelm you guys by any stretch of the imagination. What I just found was the equivalent impedance of everything to the right of this red line. Everything to the right of the red line to me looks like it's in parallel with that 25 ohm resistor. So in my calculator, I would just do 25 times answer over 25 plus answer. And I wind up getting 18.464 plus J 1.447 ohms, which exactly matches what I'm supposed to get. We went through that rather quickly, but I'm more than happy to answer any questions that you guys might have about how I did any of those steps. But the key here really is once we convert everything to an impedance, this is just resistor combination using complex numbers. All right, so any questions about this impedance combination problem? Okay, so I want us to go back really quickly here. And I want us to revisit that first problem that we worked. So we had a current source IS of T connected in series with a 5 ohm resistance and a half a Henry inductance. We're trying to find the voltage drop across our source and, IS of T is equal to 2 cosine 5t plus 0 degrees amps. And our goal was to find the S of t. So what I want us to do is to convert this circuit from the time domain into the frequency domain. Okay. So none of the elements themselves are going to change. But what we're going to do is, instead of using that cosine function for is of t, we're instead going to replace that with a phasor. So what would the phasor equivalent of 2 cosine 5t plus 0 degrees be?
Is it not just 2 angle sine and then 0 degrees?
It is indeed just 2 angle 0 degrees. What is the impedance of the 5 ohm resistor?
Five ohms.
Exactly right. What would the impedance of the half Henry inductance be? So just to remind you guys, the equation for the impedance of an inductor is just j omega L. So that's going to be J times, so what's omega here?
Zero degrees.
So 0 degrees is a phase angle. Omega is always the thing that's multiplying by t inside of our cosine function. In this case, 5 radians per second. So omega is 5. L is 0.5. So what's that come out to be?
2.5, J?
Yep, so J 2.5 ohms. So if we're trying to find this phasor voltage Vs, how might we do that just using good old-fashioned circuit analysis techniques?
5 ohms plus 2.5 J ohms times your amperage.
Exactly right. So just Ohm's law. The voltage that we're looking for is just the current times the equivalent impedance. So Vs would just be 2 angle 0 degrees amps times 5 plus J 2.5 ohms. So when I put that in my calculator, I get 10 plus J5 volts in rectangular, or 11.180 angle 26.565 degrees volts in polar form. How would I take this phasor voltage and convert it back into the time domain like I'm asked to up here?
It would be 11.18 cosine, and then you'd use the same that same angle, which would be 5t plus 26.565 degrees.
Exactly right. So we just fully analyzed our first circuit in the frequency domain. And I hope you guys can see that by using phasors and impedances, it is much easier than any other way we've tried to tackle this thing. Okay. So by working in the frequency domain, effectively, all we are going to do is use the exact same DC circuit analysis techniques that we learned in the first portion of this class, except that we're just going to add complex numbers. all the material that we're covering up until we get to our power relationships is literally the exact same thing we did at the beginning of class, just with complex numbers. Okay. So let's look at in-class assignment 20, problem 1, where we are asked to determine the phasor voltage drop over and the current through each of the circuit elements here using whatever analysis method that we choose. I am going to put a small caveat on that, and I am going to say that we should avoid using nodal or mesh analysis. The reason why I'm explicitly saying to avoid nodal analysis and mesh analysis is because our calculators can't solve systems of equations using complex numbers. So I want to get you guys in the habit of trying out other things. Okay. So again, I'm not trying to overwhelm you guys, but looking at this circuit as if it were just a DC circuit. So treat all of those inductors and capacitors just like they were resistors. What might you do to solve for, let's say, any of those voltages?
Ohm's law.
So could you explain things as to how you might apply Ohm's law?
So we know that the voltage drop over VL is just going to be IL or IL times whatever resistance is there. And then we also know that the voltage drop across VR1 is going to be the same voltage drop as VC and VR combined.
Okay, so I agree with everything that you have said, but I still am not fully following where you might use Ohm's law for this. So let me take what you've said, except for the whole Ohm's law thing, and let's see if we can interpret some stuff here, right? So what was said is that the voltage drop VR1 is the same thing as VC and VR2. I definitely agree with that. So I'm going to take that and effectively choose to interpret it as this 10 ohms of resistance is in parallel with this 15 minus J25 ohms of impedance. Is that an okay thing?
Yes.
Do you mean yes, or are you saying yes so that I will just continue on?
No, sir, I mean it.
Okay. So we have a voltage source and then an impedance and then an equivalent impedance over here effectively. So I feel like we could use voltage division to find VR1. And then knowing VR1, we could use voltage division again to find VC and VR2. So let's see how that pans out. Okay. You guys remember voltage division at all? Sounds like the answer to that might be no. So
I haven't
let's
done
go
it in
through
a
the
while.
basics. So my voltage VR1 will be my known voltage So that's 120 angle negative 20 degrees volts. And then I put the impedance that I want to know the voltage drop over in my numerator. So that is going to be 10 ohms in parallel with 15 minus J25. So that's going to be 10 times 15 minus J25 ohms over 10 plus 15 minus J25 ohms. And in the denominator, I just put the total series resistance seen by that voltage source. So it sees the J30 ohms first, and then it sees that parallel equivalent resistance of everything on the right. So 10 plus 15 minus J25. Okay. I'm going to use the calculator on screen so that you guys can all see what it is that I am doing. I'm just trying to make this sized so that I can actually see the math. So let me clear all this stuff out, clear that jibber jabber as well. So 120 angle negative 20 degrees. And I'm going to multiply that by, so I'm going to use my fraction thing here, and I'm going to have a fraction in the numerator, so I'm going to hit the fraction button again. So this is going to look like 10 times 15 minus 25i over 10 plus 15 minus 25i. And then down here in my denominator, I'm going to have 30i plus, and then all that stuff that I put in the numerator. So 10 times 15 minus 25i over 10 plus 15 minus 25i. Close parentheses. And I got 33.981 with an angle of, did I get 33 or 3 point? Negative 108.0908. So negative 108.091. There we go. Yep. So 33.981 angle negative 108.091 degrees volts. So voltage division seems to work perfectly well in the frequency domain. Now that I know that particular voltage, what else could I do?
You can multiply it by the resistance to get the current. Or you can go back doing the voltage division for the other one.
So you made a tiny mistake there because voltage times impedance is not current. It's Ohm's
Sorry,
law, so
divided.
voltage divided by impedance. Absolutely right. So IR1 would just be VR1 over 10 ohms. So that's easy enough. I just move the decimal place one over. So that's 3.398 with an angle of negative 108.091 degrees volts. We could just as easily do voltage division again to find VC or VR2. So let's do that, I guess. So VC would be VR1 times, so what should go in the numerator? If we're finding this voltage using voltage division.
The negative J25.
Negative J25, absolutely right. And what would go in the denominator?
Negative J25 plus 15 ohms.
Yep, so I'm just going to write that as 15 minus J25. Absolutely right. And so we can throw that into our calculator pretty easily. So I'm just going to take that answer, multiply it by negative J25 in the numerator, I think. We get 29.139 angle negative 139.055. So degrees, volts, which, oops, sorry, I put that as units of volts when it should have been amp because we're dealing with current, but that pretty much matches what we have there. I'm off by 1,000. So from here, we could figure out IC. So that would just be whatever VC is divided by the impedance of our capacitor, which would just be negative J25 ohms. Can't do that one quite as easily as in my head. Let me store that as X just so we can use it again in a moment. Actually, let me store that as Y. Let me go back up here. Take that thing and store it as X. Okay, so Y divided by minus 25I comes out to be 1.165 angle negative 49.055 degrees amps, which agrees with what we have there, so that's fine. That voltage drop VR2, just to be lazy, would just be that exact same current that we just found times 15 ohms. So if I just multiply this by 15, I get 17.483 angle negative 49.055 degrees volts. Seems to be legit. IC is the exact same thing as IR2 because those two elements are connected in series. So based on everything that I now know, how would I find IL, VL, or IS?
Ohm's law.
I'm sorry, what was that, Austin?
Ohm's law.
Again, could you specify how we might use it?
I'm sorry, I was looking at IC.
So I have a couple of different thoughts here, okay? So if we were to apply Kirchhoff's current law at this node, we could say that IL is equal to IR1, which we know, plus IC. Or if we did Kirchhoff's voltage law, we could say that VL is just our source voltage minus VR1. So that's two different ways to effectively get things. So like if we knew that current, then VL is just IL times the impedance of our inductance. If we found the voltage first, then we could just say that IL was VL over ZL, right? So either using Kirchhoff's current law at that node to solve for the current first, and then use Ohm's law to find the voltage, or use Kirchhoff's voltage law around the circuit to find VL, our only unknown voltage at this point, and then use Ohm's law to find the current. Just because we are running out of time, I'll leave that to you guys to actually do that small amount of math. What's the relationship, for what it's worth, between IL and IS?
It's just the negative of its magnitude.
Exactly right. So it's just the same current, but in the opposite direction. So that is 100% why, if we look at this, IS has a magnitude of 4.121 and IL has a magnitude of 4.121, but their phase angles are different because they're in opposite directions. So there's 180 degrees of phase difference between them. So multiplying by a factor of -1 is the same thing as changing the angle by plus or minus 180 degrees. All right. I would like it if you guys were to, finish up this in-class assignment problem on your own and attempt problem 2. I will probably work problem 2 with you guys at the beginning of the next class meeting. But I would like it if you just gave it a whirl, just give it a try to work a problem on your own before our next class meeting. So typically what I do for the next class meeting is ask you guys which topics that we covered at the beginning of class you would like to review. So talking about things like superposition, voltage division, current division, source transformations, things like that. Do you guys need a review on any of those topics? Your lack of a response says that you don't necessarily need a review. So what we will dedicate our next class meeting to is just working example problems of solving circuits in the frequency domain. So we're just going to work several problems until either you guys get bored or I do. And that'll be our Friday class. All right. If anybody has any questions, I would be more than happy to answer them before I have to go jump into a meeting at 4. If not, I will see you guys on Friday.
I had a quick question, Dr. Hartman.
Yep, I see one in chat as well. So Jared asked if we could review current and voltage division. Jared, I would be happy to do so. So I'll make sure to use current and voltage division in an example problem on Friday. Austin, what was your question?
I was just gonna ask about the current and voltage frequencies being out of phase.
Okay.
Is that something that, because I'm drawing my knowledge off of the real world as well, but there was an incident back in 2003 where there was a big blackout in the Northeast. Is that being out of phase can cause power outages?
No. So we're going to talk about things like that a little bit when we get into the power portion of our discussion for sinusoidally excited systems. But effectively, blackouts and brownouts occur if there's no like weather event that's knocking down lines or anything like that. They're typically related to not having enough effectively temporary energy storage in the system. So when we get to talking about complex power, we are going to cover a topic called so average power is the real part of complex power, and what's called reactive power, and it's associated with both capacitance and inductance, is the imaginary part of complex power. And what it represents is the amount of temporary energy storage in the system. So without enough imaginary portion of the complex power, our grid can't ride through large changes in the voltage that's present. And if it dips too low because too many people are drawing too much power at the same time, that's what causes a blackout.
Makes sense.
Yep. But we're not quite ready to go full on into our power relationships and all of that kind of stuff just yet. That's right, my phone just randomly started playing an old Chicago song. All right, any other questions? All righty, well, you guys have a great rest of your afternoon, and I will see you Friday.